So did anybody bother going through Grover's at all or no?
I did a little bit source algorithm and Grover's algorithm.
So you have gone through them?
Yes, just few YouTube videos actually. Just quickly go through this.
Okay, so at least.
So it's the time.
At least there's some understanding.
Yes, it is finding the time complexity to find the 2 to the power n. I mean, if any number is expressed as 2 to the power n, then it is trying to find out the time complexity, right?
Yes, yes. See, yeah, absolutely. So normally the time complexity is exponential or order of n.
Yes.
So from order of n, you are trying to minimize it to order of root n. See, if you actually look at it, all of computer science is only this. This is all that there is, right? So computer scientists are, that's why painful people, you always take the worst case scenario and then try and kind of get it to either constant time or something lesser than order of n. Okay. Order of polynomial of n is good, right? So anything you can do better is kind of considered good. In fact, actually in classical, order of n is not considered bad. In classical computers, order of n is good. You are more worried about these sort of timeline. Exponential.
Yes. Order of n squared or n cubed.
Something exponential in the order of n is what you worry about. Polynomial will generally go up, but go up much more decently, so to speak. Of course, if you have constant time, that is brilliant. But constant time is very, very difficult to achieve in any sort of computational. All of computer science is just this. And of course, we are not talking about space complexity here because the cost of memory and RAM has fallen so much over the last few decades that people nowadays talk only about time complexity. But actually, you have to talk about both space and time complexity if you are really trying to do this, right? Back in the olden days, space complexity was also important. Now to itna nahi. But anyway, 31. So let's start. I won't repeat everything that I have said last time because I wanted to get through at least part of shores also today. So I will not repeat everything, but basic idea of Grover's algorithm is clear. I will not again go through. It's fundamentally you have some ordered set of elements, whatever 1, 3, 7, 7, 4, 6, something like this, and the idea is to find one of them. Right, find whichever, find 6 for example, okay, or something like this. Normally, how do you do? Normally, you just go and start comparing and then see whatever. So, if there are n elements on an average, you will take n by 2. Correct, half the things. Best case will be right. The first one will be the one that you want. This is of course an unsorted list. The worst case is you have to traverse all n. The worst case, so it's basically order of n. So this is what this is. So can you improve on this is the quantum computing question. Can you improve on this and kind of figure it out faster? And we see that you can do it. Again, conceptually, if you want to understand, there are 2 steps to this, right? Last time that I talked about. So inversion and inversion about the mean. So those are the 2 things that you do. Again, just very quickly, conceptually very easy to understand. There is nothing, right? If you take the uniform superposition of all the qubits, then this is the uniform superposition, right? All of them have the same probability. If it is 0 to n minus 1 or whatever, then or 0 to, usually convention is n minus 1. You can write n minus 1 or n minus 1. 1 by root m. 1 by root m is the amplitude. Because the probability is 1 by m, square root of amplitude, square of amplitude, right? So 1 by root m, whatever, sigma alpha x if you take the inputs as all x's, right? So this is what this is. And what do you do? Let us say this is 0, this is m minus 1, 1, 2, uniform amplitude for everything. First step I said was very, very simple. You do an inversion about the mean, inversion, phase inversion for the one that you want to find. So whatever, let us say one of them is x star. Right, this is the, let us say the amplitude, and this probably is your whatever is your line. Then this is the amplitude. This will be what, x star minus 1. This will be what, x star plus 1. 2 elements, 3 elements, and then you simply invert the amplitude of this one. That's the first step you do. You inverse the amplitude of the one that you want. Okay, how you do it, we'll see. That also I talked about last time, but anyway, we'll actually inverse the amplitude. So what does the mean now become? Slightly less than, right? This was the original mean. Correct? Now one of them you inversed the amplitude. So if this was all, let us say there are 100 units. There are 100, okay, m or whatever. There are 100 elements. Then each one had an amplitude of what? 1 by root m. Correct. So this is some 1 by 10. Okay, this is some 1 by 10. For one of those you took and made it minus 1 by 10. You reverse it the amplitude of that one that you actually wanted. So the overall thing will become slightly less than 1 by 10.
Yes.
It will probably become 1 by 11 or something. It will become slightly lesser, no?
Yes.
Because one of them. Clear?
Yes.
So till this point, there is nothing confusion, right? Second step is, this is step 1 that you do in your Grover's algorithm. What is step 2? Step 2 is inversion about the mean. Second step is inversion about the mean. So when you actually see this, what happens? Like when you're saying the mean is something like this, then probably the amplitudes are actually something like this, right? The mean amplitude is this. So everything is, so the actual amplitudes of those photons, electrons is some way like this. So you're getting the mean amplitude to be 1 by root m or something. So when you inverse about the mean, what happens? Everything goes inverse, right? Inverse about the mean. So inverse about the mean, if you really look at it, for each alpha m is 2 mu minus alpha m minus alpha, the original m. This is the after the inversion. This can be written as mu plus mu minus this. Correct. The average plus whatever is the difference is what you invert. You invert. You simply invert across the mean, over the mean. So that's it. So that's what you kind of do. So if you do these two things, what happens now? If you invert this one becomes much higher up, right? Because if you invert this to the move, this will actually now go much higher. How much higher this will go? This step plus this step plus the mean. So it will get inverted, right? So if you do these two exercises, what happens? The amplitude of this becomes higher than all the others, right? What you essentially want to make the amplitude of the x star higher. That's what you want to do, so that when you actually do the measurement, you will find x star. Right. So how do you do that? You keep doing these two processes continuously. You will keep increasing the amplitude, and then at some point, this becomes the amplitude becomes 1 by root 2, or the probability becomes half. When the probability becomes half, then you know that if you get it right. If you run it 2 times, that time the experiment, you are pretty sure that you're getting the right answer. So that is the conceptual understanding of Grover's algorithm. conceptual understanding of Grover's algorithm, that's the genius of it. It's pretty simple, but look at how neat, looks like magic. All that guy does is you have a uniform superposition of qubits. Everything has the same amplitude. Okay. What you're essentially saying, for the one that I'm interested in, where the f of x has to be 1. Right? Because f of x is 0 for all other things, and you define the function such that function of that particular, the output will be 1. Where the output will be 1, for that one, inverse the phase, and then do an inversion about the mean. Once you inverse the phase, the mean comes down a little, then you inverse it along the mean. You do these two processes, the amplitude of the x star increases. You keep doing that repeatedly. How many number of times? It actually happens that if you do root n times, the probability will come to 1 by 2. Again, I proved it last time. You can look at the proof. It will come to 1 by root. Just have to do root n. So if n is 100, do 10 times. If you do 10 times, this probability amplitude of this x star will get to 1 by root. So if you measure it once, you may not get x star, you may get whatever, a star. But next time, if you do both times, it's more or less guaranteed at least one of the times it will be x star. So even at the end, you do it 3-4 times, it's still constant time only, right? You're not going to lose that much. It may be constant time, maybe instead of once. Somebody asked me once I was teaching this, at the end of it, you're getting the probability to have what good. You may still get or not get the right answer. Yes, you are right. But then you do it twice, thrice, 4 times, you are more or less guaranteed to get it. Because the amplitude you increase to 1 by root. This is the fun part of it.
10 is time.
Root n is the time, because by root n times you will get it to 1 by root 2. The amplitude will get to 1 by root. So that is why root n is the time complexity of Grover's algorithm, and it is a
Will it work for multiple steps?
no. I think it will, but that will work better than root n. No. See, for example, if you have 1, 5, 7, 7, 4. And let us say you want to find 7. Okay. The chance of finding it is better than finding 4, no? Because there are already 2 7s. So we are talking about the worst case scenario. The worst case scenario is only when there is one unique thing you want to find. If there is more than one, it will work. But the time complexity will only be better. It will not be worse. Because you stop once you get 1. You don't care about getting 2. If you have to get both, then that's a different problem. Then that is a different problem. But if you have more than 1, the time complexity will be lower only. It will not be higher. And I talked about phase inversion. I talked about CZ gate last time. Okay, there is a traditional CZ gate, XOR gate within quantum mechanics, and you can implement the phase inversion using a CZ gate. Okay, simply if you install Qiskit or something and practice, it's just you can just say CZ gate and you'll get the phase inversion. That's all. There's an available quantum gate. Okay, last time I talked about that. Inversion about the mean, I started, I did not finish. So today I will probably finish how do you actually implement inversion about the mean, right? Last time I explained to you the logic of how you do it. What is the conceptual understanding? Because that is more important. If you are conceptually not clear of why this works, then there's no point. See, all quantum algorithms are basically very, very simple at their heart. You have to increase the amplitude of what you want and decrease the amplitude of everything that you don't want. That's all. And you have to do that repeatedly. All quantum algorithms you will see will do exactly the same thing. Now, how you achieve it slightly differs from algorithm to algorithm, but the point is very simple. And all of this is possible because of superposition. Because at the same time, everything is in every state. So the parallelism, like I kept saying, is inherent in quantum because they are all, till you measure, it's in both states simultaneously. So you don't have to worry about that. Right? Okay. Shor's algorithm will actually be more fun than this because that actually, even after all these years, I have been studying it for 2 years now, and still that is like magic only how it works. It will be like, when I tell you how it is able to factorize, how does it actually work? Yes, I know all the pieces, but okay. So what is inversion about the mean? So what is mean? If you kind of think about mean is nothing but if you have n elements, it is just 1 by root n sigma x alpha x. Oh, okay, no alpha x, sorry. Alpha x is weighted mean. No weighted mean. Normal mean. Right. This is the mean of x, right? That vector x. So you're trying to reflect on the mean. That's what I said. Inversion can be seen as a reflection. When you're inverting, inversion can be seen as a reflection, right? So a reflection on this. This you can call u. So if you have some vector psi is again 1 by root n. Or maybe we need not assume uniform superposition at this point. So let us not assume, because one of them we have inverted. So we cannot assume uniform superposition because it's not uniform. Right. So it is basically what? X is equal to 0 to n minus 1, alpha x, x. This is your original vector. This is your original vector that I drew. Okay, where some alpha x's, for one of them where x equals x star, the alpha x is negative. But everything else, it's the same thing. So this is the mean. This is the vector. And you have to reflect this on that. That is the inversion about the mean. Correct? So if you diagrammatically see this, let this be some vector psi. Okay. Let this be some vector u, which we call mean now. The mean. Then you have to reflect this on this. You reflect this on this, then it becomes a inversion. Right? So how do you do that? There are many ways to do that. Okay, this is where I said go read some basic complex analysis. The easiest way to do this is create a vector orthogonal to u. Okay, call it V. Psi. Now there is a component of psi on V and some component of psi on u. So u and v can become basis vectors. They are orthogonal basis vectors for this psi. Then simply invert the phase of V. And within that, the component of psi also. Now you have this component of psi and this component of psi. So you have taken the negative of that. Then if you resolve that onto this, the negative component of psi on u, what you get is reflection. So this is there is an actual theorem around this that you can prove. Okay, in complex analysis, there is an actual theorem around this that you can actually prove. But for now, take my word. Otherwise, we have to prove that theorem. Okay, but if you go and read any complex analysis book, this is how you reflect vectors. Okay, in fact, you can even read it in real analysis also. Okay, real analysis also you have the same theorem. Instead of complex space, you can do it in real space. The only reason why we do it in complex space because these alpha x's are complex numbers here, right? Because this is qubits, quantum mechanics. So these are complex numbers. These alpha x's are all alpha x belong to C. I can prove the same belonging to R. Where alpha x's belong to R, also the same theorem will hold. Again, if you remember, I talked about some of these when I talked about complex numbers, but don't want to embarrass anybody by going back. But that is what it is. Okay. Now, but how do you actually do it? Okay, so this is the conceptually how you do it, right? Now, how do you actually do this? Conceptually, it's clear, right? What is reflection? It is nothing very great. And if you can keep on doing the inversion and reflection root n number of times, you will get the amplitude to 1 by root. That's all. Now, how do you do? The simplest way to do this is, first thing, transform, and this is just because it's mathematically easy. Okay. U to the zero vector. So make everything into zeros. Make all the amplitudes, make them all the zero vector. Okay, so just do a unitary transformation. It's actually nothing but a Hadamard transformation. See, and Hadamard transformation, another thing probably I didn't tell you, which maybe when you have time I will go through this. A Hadamard transformation can also be in some books, you will see it referred to as the Fourier transform. So a Hadamard transform, if you remember, which is nothing but 1 by root 2, 1 by root 2, 1 by root 2, minus 1 by root 2. This is the unitary transformation, right? This is the kernel. This is the unitary transformation that you put on something to do a Hadamard transformation. It can be proven that this, once you do this transformation, it is similar to sampling from a Fourier transformation of the same vector. Okay, it can be proven. Of course, I have not proven that. We can prove it. In some class, I will prove it to you that this also means this particular transformation is equivalent to doing a Fourier transformation of the given signal or the given vector. Okay. So some people in some textbooks you will see do a Fourier transform. It's nothing but the Hadamard transform. Okay. It depends where you are coming from. If you are coming from signal processing and mathematics, you will study this as a Fourier transform in complex analysis. If you come from a computer science background, you will call it a Hadamard transformation. Okay. See, a lot of things in math are like that. Depends on which subject you have studied. You will talk about it differently. But data scientists, the tragedy is you need to know both. Data scientists, you need to be able to know the computer science back terminology as well as the mathematics terminology, because we will be asked to defend things in both scenarios. Sometimes I have to present to a mathematician, sometimes I end up presenting to a thing, sometimes I end up presenting to a business case, in which case both of those are not relevant. I just don't tell him how much money that will make. But having said that, that is the way it is. Okay, so first you transform, second you do the reflection. What I talked about, right? Kind of do the thing, orthogonal and all of that thing. Third, transform it back. Because I got to transform back, right? To get the actual value of psi hash. Transform. This is it. And also get very, very familiar. Start writing. Get familiar with get and bra and these notations. Okay, when you are actually writing, dot products and things like that. Because I have been doing all of this, and tomorrow you shouldn't say you attended some quantum class and you get confused on how to write a ket or a bra or something. So practice that writing, but it's okay. Don't get too worried about it. So let's talk about reflection. Let's see how I will not solve the whole thing, but let's see how the matrices look. How does the unitary operator look for reflect? These are simple. These are just Hadamard transforms. There is nothing great. It's just a n-bit Hadamard transform, right? So we saw it for 2, but if you have n, you have n. It's the same thing done n times. Okay. And do these things in practice. So for example, you have what? 1 by root 2, 1 by root 2, 1 by root 2 minus 1 by root 2. What happens if I multiply two of these? So if I have to do it for 3-bit or 4-bit or 5-bit, okay, just do it for a few bits so that you convince yourself. So essentially it will be the same here, same here, same here. Here will be negative of the same, right? Because it's a tensor product of these two. So you just have to convince yourself that those multiplications work. Okay. I don't have to do that in class or something because those are simple things. Just multiply and see. Just tensor products. Nothing much to. Okay, so let's see what does reflect on this mean. So it's n. The first one you leave as 1 because it is the zeros you leave as it is. Everything else you transform, right? You don't transfer. You're trying to reflect on this. So the first one you leave as it is, the first diagonal, everything, all other diagonals will be minus 1s. Because you are trying to reflect.
Yes, yes.
Okay, so everything else will be minus 1, minus 1, minus 1, minus 1, whatever. The size of the. Good, check it out. Then you just fill the rest of the matrix. So this is the transformation, the unitary. When I say reflect, this is the transformation, and then we can do a few things. Of course, you can do the Hadamard's and all. You forget about the Hadamard's too much. You don't have to remember that. But because there's one Hadamard here and one Hadamard here. This is one end. But this is the actual matrix. Now the trick is, there is a certain trick to this, okay, and I will not go through. I'll tell you the trick though, because that's important. Because finally this has to come to 2 mu minus x, right? I wrote alpha x equals 2 mu minus alpha x, right? So finally this has to break down into that, because that is what you got to do here. I said this is the reflection, and I've written that this is the matrix for the reflection. Now I have to somehow prove to you that this matrix will do the same operation as this. Yeah, so ikkade matrices get fun as usual. But you can prove it. No, don't worry. It will get there. Yeah. Ikkade oka trick ante malla you go back to intermediate. See, you saw a 2 there. So there has to be a 2 somewhere here. Otherwise, how do you get 2? So how do you get 2 here? Subtract an identity matrix out of this, you get 2 here. You get zeros here. Minus identity, right?
Yes, yes, yes.
That's what I'm saying. Finally, it is like intermediate math only. You have to take this, you have to prove 2 mu minus x. You are thinking alpha x is easy to prove. Somewhere here you have to get 2 mu here. How will I get 2 mu? First problem I have to solve is get 2. Then I will get mu. Then I will get 2 mu. See, that is why people who say math is difficult, it is not difficult. It is just common sense. You want 2, you want 2 here. What the hell? I need 2. Kahan se leke aunga 2? You put 2 here, you subtract 1. Then you bring 2. What is the big thing? Nothing is difficult. It is just thinking.
Here are the equations, multiply the whole equation by 2 by 2.
Oh, exactly.
Yes, yes.
You don't know, you're multiplying lot of numbers, take a log. And nothing, everybody does the same thing. So you put the same thing. Now I don't know if I want to solve the whole thing, but yeah.
Balance the equation.
You put 2. Then everything minus 1 plus 1, everything becomes 0. Correct? Or whatever. All of these, of course, will become same. ఇప్పుడు దీన్ని బ్రేక్ చేసుకుంటే see after this it is just a manipulation, do a manipulation, okay, multiply this into this and this into this. If you do all of that, finally you will get 2 mu minus alpha x. I'm not going to waste a lot of time. Some of you try this. If you can't get it, next class you tell me, I will do it. Okay, but it is just matrix multiplication from this end on. Okay, there is nothing. You just have to do a few matrix manipulations. It is not simple still, but it is doable. Okay, it is doable, and I think a lot of people have left. Everybody has left basically. Okay, you and you only are left. Okay, you two only are there. Okay, so this is so this kind of proves it. So the overall matrix, as you the overall thing that if you see end-to-end Grover's algorithm, you got the CZ gate. See, the overall thing, if you look at it, you have the CZ gate to do the inversion, and then you got Hadamard. And then you've got this U of F, which is this big matrix, again Hadamard gate. Okay. And then you just repeat this process root n times. Then you measure after the Hadamard, and you should get your answer. It's as simple as that. And think about it. This is revolutionary. Imagine if you can implement it. Imagine what you can do to global search. Any search, Google search algorithm. If you can quantize this algorithm exists. The only problem is we're still not at that enough level of qubits to actually implement it. Because if you implement it, your search becomes root n times faster. The entire globe, everything you can search root n times faster if you have this algorithm. Right? So it's very, very powerful. There was actually a tweet by Elon Musk a 1 year ago or something. There was some dude who asked him, I want to make $1 trillion. What should you do? He said, implement Grover's algorithm. Street, he said, implement Grover's algorithm. You'll make $1 trillion because you implement this shit, all search in the world is root n times faster. Everybody's on it. See, this algorithm was in 1990s by Love Grover. The algorithm was in 1990, something, somewhere 1990s. Okay. By a person called Love Grover. Yeah, so that was the guy who put it. 86, yeah? 96, yeah, somewhere in the 90s is what this guy did. And then post that, of course, all hell broke loose and people are trying. So everybody's trying. But even small subsets of this are very, very useful because root n is very, very huge, right? Especially when you're talking about a lot of data. Root n becomes extremely, extremely important. Okay. So this is an idea of Grover's algorithm. I think post that we'll talk sure. After that, I will come back and actually implement this in Qiskit on classical thing. Post that is done, we will go into machine learning algorithms. Maybe there's 1 or 2 more Simon's algorithm. Maybe if we have time, we can go to Simon's, and after that we just get into start implementing some linear regression or logistic regression using quantum, and then see what does that mean. Because what I want to do is once we implemented this with Qiskit or something, which is a simulation, you cannot on your laptops, you will not be able to do more than 5-6 qubit systems because that is the whole reason why we have quantum computing, right? Richard Feynman said it's not possible to simulate a quantum mechanical world using classical physics. It's just way too much compute intensive. You actually can't. So once you do that, then for the next session, let's take we'll spend some money. Let's take on IBM's quantum computer packet. You can actually buy some time. Right now it's beta, so they're giving it still for free. So you can take that and then actually run it on a proper 20-bit, 30-bit system and see what happens. Because then it's an actual quantum packet, okay, not a simulator. At first, it's better to do it on a simulator to get your gates and things right, rather than doing it on, first get your gate circuits right here, and then you can. Yeah. So now what is it? Show the great man. I think this is the algorithm that actually made quantum computing popular, right? everybody is on this. Everybody is on this because this is the algorithm that's supposed to break encryption, break the world, destroy the world. Factorization, right? Factorization, basically factorization. So what is it? You take some number, right? N equals, let's say 60, some number, take some number. What is this? If you take 60, what are the prime factors of 60? It is what? It is 3. 3 is there. 5 is also there, right? Into 2 square. So something like this. These are the prime factors of 60, right? So the idea is you can take any number and write it as some sort of P1 to the power E1, P2 to the power E2, Pk to the power Ek, such that P1, P2, Pk are all prime. This is the whole prime factorization problem, mathematically. Now we struggle doing this, right? We really struggle doing this. So classically, it is all 2 to the power n, where n is the number of bits. So if n is the number, then it's a, let's say you take n equals 1000. So it is a 1000-digit number. If you have a 1000-digit number, it is approximately what, 10 to the power 1000 is the value of the number. It's a very big number. So you want to do something like this, then the order, the time complexity is something like 2 to the power 1000. Very big. Okay, so no way in hell can we do anything like this. So this is the basic problem, right? Of this also, strangely enough, the most difficult problem happens to be where the number is a multiple of 2 primes. It's called the twin prime conjecture, twin prime problem. Okay, no, this is a difficult enough problem, okay? But the toughest even among this is when n is of such that it is a product of 2 primes, and each prime being more or less of equal length. This is the toughest of the all sorts of prime factorization problems that exist in the universe of prime factorization. This is the king of them all. And we struggle. We cannot. The entire RSA is this way. The entire RSA algorithm, the public key algorithm of RSA is based on this. That it is near impossible to factorize a number into its primes. But given 2 primes, to check whether it is these are factors of this number or not is trivial. See, it is a type of problem where going from here to here is impossible. Going from here to here is trivial. Right? It's one of those problems, and that is the exact problem that you want. So that's why it is perfect for any sort of encryption. Because if given these two, you can easily get, but given this, there's no way in hell you can get these two. It is so very difficult to actually compute. Think about the genius of this problem.
That's how you know the store of credentials.
Whether it's credit cards, e-commerce, internet, the whole thing runs on just this simple property of prime factorization. That is all that there is now. And the whole idea is the Shor's algorithm says, see, computer scientists and mathematicians have been on it for decades, for centuries actually. And the best we can get even today, best algorithm in the world that we can get is 2 to the power of order of cube root of n. It's still horrible. It's still horrible. Right? Cube root of n is probably the best. If you have a 1000-digit number, it still comes to a huge thing. Cube root is probably still a 300-digit number, still way beyond our classical sort of things. But at least this is the best. In cube root of n, there are algorithms, but these use such horrible, not horrible, such complex number theory sort of theorems and nuances to get here. So having said that, I think now I have set the context to say classical doesn't work in this case. Now, let us try and kind of see. Before that, we have to do one thing. We have to learn one thing before we get there, which is basically called period finding. Okay, let's talk about that problem first, because that will be required to understand Shor's algorithm. We'll do that first, and then we'll get into Shor's algorithm. Again, absolute genius devised this in 80s, and this is the one that actually said that quantum computing can have some real value. Because till that point, it was just Richard Feynman's thing saying that, hey, our world is quantum mechanical, our computers are classical, so this is stupid. So that's what Feynman's thing was, right? He basically said all of this is a waste of time because we cannot really simulate anything useful. Because your world is basically quantum mechanical. Why are you sitting with classical machines? But nobody was interested because yes, that is true, but why is anybody bothered about that? Okay, the world is quantum mechanical, fine. But with this algorithm, Shor finally proved that you can solve a problem. And see, the other problem with other interesting thing, I don't know if you guys know this, but we will not get into this, but P equals NP problem, right? P equals NP problem, which is polynomial time, non-polynomial deterministic. So the idea is, if there is one NP problem that you prove can be solved in polynomial time, then there is not a theorem, an understanding among mathematicians saying that all NP problems can then be solved. The idea is all non-polynomial deterministic problems are somehow equivalent. There is an equivariance between them. So if you solve one of them in polynomial, if you can prove that you can solve one of them in polynomial deterministic time, that means every single one of them can be solved in polynomial deterministic. Okay, and that's groundbreaking. So if you can actually solve prime factorization, which is known by everybody as a non-polynomial deterministic time problem in polynomial time, then everything, starting from a traveling salesman problem to everything, can now be solved in polynomial. Of course, so it opens literally a Pandora's box of what we're talking about, right? So it means we can now pretty much solve any problem that we want to solve. Okay. Yeah, let us talk a little mathematically. I think I have talked enough about as a layman. So what is period finding? Okay, let's talk about this. What is the period finding problem and how do you go about solving that classically? Input given some f. Mapped into some set A such that for all fx plus r equals f of x. Okay. Such that there is some r, some periodicity at which the same value keep repeating. So the challenge is, if I give you something like this and if I say find r, how do you do that? Right. That's the challenge. If you really see this problem in another way, this is also, because you are all machine learning people, this is also the fundamental problem of all time series analysis. All time series analysis that you see is kind of the same problem. What is the time? 12:13. Maybe we are going overboard. I don't know, maybe for 2-3 minutes and then I will, because I'm getting a lot of messages on Teams. I think people are right. So you understand, right? This is a complex problem. So if you really see something, and it's just for you to understand, if I actually draw something like this, yeah, and then let's say this is x, and this is as usual f of x. We are always be talking 2 dimensions because it's simple to draw, but nothing in life is 2 dimensional.
Sir, laptop alignment is not proper.
Oh, sorry.
No, it's fine.
Sorry. Sorry about that. If I have something like this, right? If I have something like this repeating, then this is what I call the cycle. So this is called the cycle, right? So the same values keep repeating. Okay, so I don't know, some period equals 5 or something. If you take an m equals 100, then you can say you will have 20 such observations, 20 such repetitions. Every 5 times you have a total of 100 or whatever like that. Here we will make one simplistic assumption. Later on, I'll tell you that the assumption may not be required, but I will take it because some understanding becomes simple. We will say right now for our understanding that R divides N. That means if it's 100, this is not the 3. Then if it's 100, it's 4 or 5 or something. Which divides, maybe 6, maybe 10, maybe not 6. So R divides M. R is the period. M is the total number of observations. And I'm saying it actually divides. Also, we will make another assumption, which is probably useful, is M by R is much, much greater than R, or M is much, much greater than R square. So what I'm saying is the number of observations is much larger than the actual period. Okay. Again, these are just some simplifying assumptions to do this. If it is not, also it works, but just there is a little more drama that you have to do to make this work. So I'll just see the problem with this in the classical world and then leave. Next session we'll probably do. We won't wait for weeks and weeks, maybe whatever. Today is what? Thursday. So next Monday or Tuesday we'll have that. I don't want to, otherwise, I don't know how long we will keep doing this. I want to get down the basics and actually get to properly doing something, right? So if you look at the classical world, how will this problem be given? Let's say it's some classical circuit, you got XS, and then you'll have f of x. Right? So let us say M is like I said, 1,000-digit number. So basically M is approximately 10 to the power 1,000. Is kind of the value, right? Now we are saying M is much, much greater than R square, so probably R is somewhere near square root of M. Even if you assume this, R is what? Square root of M. That means it's a 500-digit number. Right, 1,000-digit number, it's a 500-digit number, maybe up to 500. Of course, it can be a 3-digit number also. But let's say it's a huge number still. Classically, we will still kind of struggle, right? And how do you even find this? If I say find R, if I give you something like this, a 1,000-digit number, and if I say find R, how will you find it? In the classical world, the only thing is you have to randomly keep doing stuff till maybe at some point you hit F, and then you hit f of x and f of y, and both of them are same. If there is some collision, then it gives you some information. Okay, and then you have to randomly keep doing that up to this bigger scale for you to actually determine that this is the smallest cycle that is out there, which is really ridiculous. Okay. Actually, there is a problem. How many times you have to do the minimum that you have to do to get to that? If you randomly do, how many times you have to do this? It typically is about root r times, which still is somewhere near 10 to the power 250. Still a 250-digit number, which is way outside our scope any which way. But why is this root r is an interesting thing. Do you guys know the birthday paradox? Do you guys know the birthday paradox? if I ask you, how many people do you think you need to have in a room? Okay, how many people do you think you need to have in a room so that two people in the room, there is a 50% chance that two people in the room will have the same birthday. Assume 365 days, don't assume 360 days. It just creates more confusion. Okay, and assume everybody has got a different birthday and things like that. Make some simplified assumptions. What does your common sense tell you? Anik, what do you think? If I ask you how many people should be in a room such that the probability of any two people having the same birthday is 50%. This is a classic. This problem generally I used to ask in interviews back when I used to do this. Okay, so how many people do you think? Guess. Okay, let me say. Is it between 200 to 300, 100 to 200, 50 to 100, or 0 to 50? अरे बाबा कुछ तो बोलो, कोई मारेगा थोड़ी ना मैं इधर. Guys, don't even guess. It's 23 people. That sounds ridiculous, right?
Yeah.
Sounds ridiculous, right? If you just have 23 people in a room, you have a chance, you have a 50% chance that at least two of them will have the same birthday. Now, on the surface of it, it looks meaningless. There are 365 days. 23 people, how can you get the probability greater than 50%? Okay. Now, I will just not solve the whole problem for you, but you can solve it. There is math to prove it, as usual. That's why follow the math. It gives you the answer. See, it's very simple. Look at the alternative. What does it take for people not to have the same birthday? See, for person one, he can be born on any of the 365 by 365 days. They are independent events. Right? One guy's birth is not influencing another guy's birth. For the second guy, it is what?
364.
By 365. For the other guy, it will be 363 by 365. If you keep doing it, 23, it will be 343. This number, if you actually calculate, okay, you can kind of say whatever. If you approximately calculate, this will be 0.49. So the probability they'll have is 1 minus 0.49, 0.5. See, I am telling you the probability of any two people. I am not telling you, for example, how many people does it take to have the same birthday as Srinivas Atreya? It's a different problem. It's a then the answer will be much, much higher. And also remember, what will be the probability that, see, with 70 people, you can get to 99.73 probability that they will have, two people will have the same birthday. The probability will go to 99.973. So very, but if you want to get it to 1, you will still need 366 people. Correct. See, that is the long tail of probabilities, not the pigeonhole problem. Okay. That's why probability is not as easy as it seems. With 70 people, you get 99.973. But if you want to be certain that the answer has to be 1, then you need 366 people at the minimum. Because there is also a chance for 365, each one having one unique birthday. Right? 366th one, guaranteed. You cannot do that. So it is, and in that long tail of probabilities where most machine learning and statistics fails. And
the rest case, you consider the leap year.
If you consider leap year also, it becomes 360. That's why I said don't consider. But that's the fun part. Okay, so here if you see, it will be approximately be root 365. Next year, 22 is not, 24 is.
20 was for the
So approximately root 365, right? Root 365 is 18 or something. So it comes to 23, order of root n. That's why I said root r. This can be generalized. This is why, that's why I said that the answer is birthday paradox. Okay. So it's not really a paradox. It is just that people get confused of probabilities. That's all. There is nothing like, there is no paradox here, actually speaking. Okay. So probability, all your life keep studying. There is nothing that I have finished probability, will never get there. So keep doing it, but it's a fun subject. So I think, so now classically we know that finding R is a near impossible problem. You cannot find R. Okay, you cannot. And if you could find R, your time series would have been a solved problem. Because then, given any time series data, I can tell you at what period will this sequence of data repeat again. So I am doing these sales, again these sales will occur exactly on this day, I can tell you that. The point is today you can't, because you cannot find period in a classical method. It takes time, it's computationally extremely complex for you to do that. Now we will show that in Shor's algorithm, you can even do that. Actually, using Shor's algorithm, you can solve a lot of problems like that. Quantum computing is an interesting world. That's why it looks like magic actually when I show you how this works. Anyway, thanks for this. And let's now, I think all of you have your day jobs. I also have presumably a day job. So I will go about to doing that. You guys can go about doing that. Anik, hopefully you enjoyed it as much as I did. Okay, take care.
Okay. Thank you, Srini. Bye bye.